Now we're going to talk about our pendulum just a little bit further. And what we discovered was that the influences of the pendulum. So, once again, what was a pendulum? So, I had this hanging and I pulled it off to the side. Okay. This thing here, by the way, is called the bob. And if I have my center point of my pendulum, let's draw that here with a nice dotted line. Okay, so there's my center line there. That's my rest position. And if I let that pendulum go, it's going to swing and it's going to end up over here. Okay. What we've learned is that, first of all, you got this angle here. We've got the length of the pendulum, and we have the mass. Now, if we go way over here, we have that free fall position. We don't want to go there. So we're going to say that the angle has to be less than 15 degrees. But otherwise, that the period of this is not influenced by the mass or the angle. Okay, it is only affected by the length. So, when they used to have grandfather clocks, this great big clock that would stand in people's houses, and they would have a pendulum here that would swing, right? So a big clock. If the clock was off in its time, too fast or too slow, they would just change the length of it. There would be a little threaded screw, and they could just twist it to adjust it slightly, and you would know which way to twist it to speed it up or slow it down, so that your clock would keep accurate time. Okay, I'm not going to go through the algebra of how to derive this equation. It's not that hard to do, but we'll skip it for today. But the period t is equal to 2 times pi times the square root of the length divided by gravity. It's a good formula to know. Let's do a couple practice questions. So here I have a mass of 1.92 kilograms being hung from a string with a length of 1.20 meters. And I want to know the period and the frequency. Now, let's see. We just found that this is 2 pi times the square root of the length divided by gravity. So that would be 2 times pi times the square root of 1.2 meters divided by 9.81 meters per second squared. If I look at my units just first here, I've got meters divided by seconds squared. When I do just the units here, I'm going to end up with the square root of seconds squared. There's my unit analysis. And that's wonderful because that's going to give us seconds, which is what we wanted. When I solve for this, I'm going to find that the period is equal to, I ended up with 2.20 seconds. Now, what about this mass? This mass is thrown in just as a distraction. That does not influence the solving of the period for this pendulum. Now, to get the frequency, we have two options. We could either take it as oops, let me just write this. The frequency is 1 over 2 pi by the square root of Lg, or which what I'm going to do is I'm going to say it's 1 over t. That looks much easier. So the frequency is 1 over 2.20 seconds. And that means that has a frequency of 0.455 hertz. I'll do one other question. What I have here is I have a pendulum with a frequency. So my frequency is 0.613 hertz. And I want to know the length. I would start off with this. If I have the frequency, I'm going to find the period. The period is 1 over the frequency. So my period is 1 over 0.613. And I'm going to take the hertz, and I'm going to write that in as seconds to the negative 1. Because I learned in Math 10 that when I have this, seconds to the negative 1, that's the same thing as saying seconds on the top to the positive 1. So 1 divided by 0.613 is going to give me a frequency, of 1.63 seconds. So that's not my final answer, but I need that to solve what I'm doing. Okay, so from there, what I have is I know that my frequency is 2 pi times the square root of L over G. Now, I prefer to do the algebra first. I know some of you are going to say, you know what, I just want to take this. So, you're going to do this. You're going to go, 1.63 seconds is 2 pi times L over 9.81. And you could solve that. But what I'm going to do is I'm going to do the algebra to start. Okay, so let's see. I'm going to take my period, divide that by 2 pi. That equals the root of L over G. So there's the algebra. I divided both sides by 2 pi. Then I'm going to get rid of the square root symbol. So if I take both sides of my equation and I square it, that will get rid of the square root symbol. Now what I can do is I can multiply both sides by g. So I'm going to get g times t squared over, I'm going to say 2 squared, that's 4 pi squared. And that will give me my length. All right, so that's not so bad. So my length here is g, 9.81 meters per second squared, multiplied by t, which here was 1.63 seconds squared, divided by 4 pi squared. Be careful with your BEDMAS order of operations. And I'm also going to look at my units here once again. I got meters over second squared times second squared. And this cancels out. I'm going to be left with meters, which is great because I was hoping that with finding length. And I'm going to find that my length here is equal to 0.6612 meters, or I'm going to say 66.1 centimeters. Now let's look again at our springs. So once again, I have a spring, and on there I put a mass. And if I pull that down, and let it go, it's going to go up and it's going to go down. Now, if there was no friction, there would be perfect conservation of mass and it would keep going up and down the same amount. But we have observed that we are losing energy due to friction and it just gets smaller and smaller. But let's pretend we have an ideal world where there's no friction and there's no weight loss in the spring and so on. This would go up and down, oscillating forever. And we could figure out the length of time that it goes up and down, just like we did with the pendulum going side to side. And there is a formula, and it looks very similar to the one we just saw, that the period is equal to 2 pi times the mass that we're using divided by the spring constant. So once again, the length is not a factor. Length, not a factor. Length, not a factor. So it doesn't matter how far you pull it down, that does not influence the time it takes to repeat. Okay? The only influence is how heavy is the weight and what is the spring constant. Okay. I want to very quickly just look at some units for a second here. And we know that our spring constant has units, newtons per meter. I'm going to break that down. What is a newton? Well, a newton was a kilogram meter per second squared. And when you take that and divide it by a meter, what's going to happen is your units of meters are going to cancel. So the spring constant, the units that we're going to use, we're using the newtons per meter, but 1 newton per meter is the same thing as saying 1 kilogram per second squared. Okay, so that's going to come into effect here when we do this, because what happens is when we look at let's just pull the formula down here again. When we look at the period is 2 pi times the square root of the mass divided by the k value. When we look at the units, what we have is, well, there's no units for pi, so t, we're hoping that's going to be in seconds. Okay, we're hoping that's going to be in seconds. Well, that's going to be 2 times pi. Well, there's no units for 2, and there's no units for pi. So when we just look at our units only, it's the square root of mass is kilograms, divided by, and our k units are kilograms per second squared. So a kilogram divided by a kilogram divided by a second squared is the same thing as a second squared. And so the units are the square root of second squareds, which are seconds. So our units work out beautifully in this equation. Let's try a question. So here I have a mass of 800 grams, and I'm right away going to convert that into kilograms. It's going to oscillate on a spring 12 times. Well, N is 12, and it takes some time, that's delta T of 18.24 seconds. And I want to find my K value. All right, I'm going to start by finding my period. So my period here would be my delta T divided by N, which is 18.24 seconds divided by 12. So my period, T, is going to calculate out to be, I'm getting 1.52 seconds. Not so bad. So now I want to know K. Well, I know that T is 2 pi times the square root of m over Okay. Now I know some of you are going to just start punching numbers in there. I'm going to do my algebra first. So let's see. I'm going to move that 2 pi to the other side. So I'm going to end up with t over 2 pi equals the root of m over k. So what do? I just divided both sides by 2 pi. Okay, there's my algebra step. Okay, and I got this. Well, now I want to get rid of that square root symbol. Switch some signs, colors. So how do I get rid of a square root? I'm going to square both sides. That's the algebra step to get rid of a square root. So now I have t squared over 4 pi squared equals m over k. All right, a little trick here. The k is on the bottom, and I got a couple different strategies I use. The one I like using is I know that if I flip over that, I can also flip over this. So that's my little flip trick. Works with fractions in algebra when you got the equal sign. Flip both sides over. There we are. Only do it if you have a fraction on both sides, or if it's something over 1. Okay, and now what I'm going to do is I'm going to multiply both sides by m, and that'll take care of the m right here. So now I have my equation to find k. K is m times 4 times pi squared over my period squared. Okay, that's not so bad. So here we go. M, 0.8 kilograms times 4 times pi. There's a button on the calculator for pi. Divided by, and my period here was 1.52 seconds squared. Once again, I'm just going to double check my units over here. So I'm going to check my units. I'm going to end up with kilograms, right? Because there's no other units here. 4 pi, no units, over seconds squared. Perfect. We looked at it a few minutes ago. That is the same thing as a Newton over meter, which is the K units that we'd like. So we see that K is going to be, and I'm seeing 13.6698. And I'm not going to say kilograms per second squared. I'm going to say newtons per meter, or 13.7 newtons per meter if I round that off to 3 significant digits.